Here's another video on connected particles. This time it's pulleys, where both strings are hanging vertically down. So here's an example of a pulley system that I am sure you are familiar with the diagram of. I just want to highlight one or 2 points in the words included in the question. So for example, a light inelastic string. If the string was not light, as a left side mass descended, you would have a greater length of string on that left side and less string on the right side. If the string doesn't have a mass, that does not matter. But if it does have a mass, what would be happening is you would be having a greater and increasing mass on the left-hand side and a shrinking mass on the right-hand side. And this would result in a change, an increase in the acceleration. So you would not have constant acceleration if the string was not light. If the pulley was not smooth, the tensions in each side of the string would not be equal. You are probably familiar that we just write the tensions in as T, T on both sides. You wouldn't be able to do that if the pulley was not smooth. And because the string is inelastic, the magnitude of the accelerations in each side of the strings are equal, albeit one's going up, which would be positive, one's going down, would be negative. What are the forces in the system then? Well, we can straight away put the weights on the objects. In addition to that, the strings are taut, and therefore there are equal and opposite tensions in each side of the string. So on the left-hand side, at both ends of the string on the left-hand side, acting towards the centre, equal and opposite tensions, and similarly on the right-hand side. These two tensions at the top, which highlighted yellow there, those two tensions act on the pulley, and the other two tensions, or the other tensions, are acting on each of the masses. If we apply F equals ma, i.e. Newton's second law, to the 5 kilogram mass, well, that mass is accelerating downwards, so the resultant force is going to be 5g minus t. So we end up with 5g minus t, the resultant force, equals the mass, 5, times by the acceleration. Whereas applying Newton's second law for the 3 kilogram mass, that's accelerating upwards, so the resultant force on the 3 kilogram mass is the tension T subtract 3g. So we have T subtract 3g equals 3 times A. If we add the two equations together, the T's will cancel out. We'll end up with 2g equals 8a, and so we can work out A from that, 2.45 meters per second squared. When we substitute that back into either of the two equations, we can find T, and that's 36.75 newtons. In order to calculate the force on the pulley, it's quite a common question. It's not a difficult calculation, clearly not in this case, because it's just the two tensions we can see acting on the pulley. So it's just 2 times T, and that's 73.5 newtons. So here's an example from our textbook. Find the acceleration of each mass. So we put the weights on. Q has a mass of 3m, so it has a weight of 3 mg. P has a mass of 2m, so therefore it has a weight of 2 mg. Tensions on the left side, tensions on the right side. So applying Newton's second law to Q, Q is accelerating downwards, we can see in the diagram, so the resultant force is 3 mg subtract T equals 3m the mass times acceleration, whereas P is accelerating upwards, so the resultant force on P, T subtract 2 mg equals 2m the mass times acceleration. When we add the two equations, the tensions will cancel and we're left with mg equals 5ma. Now at that point we can just divide both sides by m, we can cancel the m's, so we're left with g equals 5a, and dividing by 5 we get a equals g divided by 5, which is 1.96 meters per second squared. To find the tension in the string, well, applying Newton's second law to P, we have T minus 2mg equals 2ma. We've just calculated A to be 1.96, so we substitute that in, and that gives us 23.52 m. Note m is just included in our answer, as it says in the question, find your answer in terms of m. To find the force exerted on the pulley, once again it's those two tensions there, so it's just 2T and it's 47.04 m newtons. Find the distance travelled by Q in the first 4 seconds, assuming P does not reach the pulley. So this is a situation whereby this system is acting under an acceleration that is not 9.8. It's under a restriction, and in actual fact we've calculated the acceleration of Q to be 1.96. So initially it starts from rest, so U was 0. The acceleration is not 9.8, it's 1.96. We calculated that. The time is 4 seconds, and we want to find that distance. Using one of the Suvat equations, as you can see there, substituting our values in, and we get 15.7 meters to 3 significant figures. Part E, you often get this last part of a question. It's never really well answered by students, and these little points just really do need to be learned. State how you have used the assumption that the pulley is smooth in your calculations. The smooth pulley means I assume the tensions in both sides of the string were equal. In this section of the video, we're just having a slight increase in difficulty with the question, because what's going to happen is the heavier object will fall down and reach a horizontal surface or the floor, and then the question remains, what will happen to the lighter object when the heavier object reaches that surface? So in the diagram here, the lighter object, the 3 kilogram mass, has risen upwards, and now it's suddenly stopped, but in reality that would not happen. It's fine that the 5 kilogram mass reaches a floor and stops as a result of reaching the floor. The tension in the string will become 0, which means the 3 kilogram mass will no longer be being pulled upwards. But that doesn't mean to say it will suddenly stop moving. It will continue to move freely under gravity. It had a velocity at the point where the heavier object hit the surface. It has a velocity, so it will start travelling as a projectile would, until that velocity is exhausted by the acceleration of negative 9.8. And then it will fall back down again, and then it will continue to fall a little further because it will jerk the 5 kilogram mass back off the horizontal surface. But you're not usually asked to analyse the subsequent motion when that happens. It's usually about trying to find the maximum height that the lighter object reaches from the surface. So just to recap, in this phase of motion, the objects move under acceleration produced by the system, and then at that point, in the second phase of motion, the 3 kilogram mass continues to move as a projectile. Here's our example then. We're going to try and find the maximum height that the 3 kilogram mass reaches above the ground. Remember that when the 5 kilogram mass reaches the horizontal surface, the 3 kilogram mass will have a velocity, and we need to find that velocity to work out the distance it continues to move upwards as a projectile. Now the velocity the 3 kilogram mass acquires when the 5 kilogram mass reaches the horizontal surface is exactly the same speed with which the 5 kilogram mass reaches that horizontal surface. So that's how we're going to proceed. We want the speed with which the 5 kilogram mass reaches the horizontal surface. So we need the acceleration, so let's put the forces into our diagram. We've got the weight, the tension, and applying Newton's second law to the 5 kilogram mass, we're going to have 5g subtract t, that's the resultant force, equals mass times acceleration. For the 3 kilogram mass, which is accelerating upwards, the resultant force will be t minus 3g, and that equals mass times acceleration. When we add the two equations, we get A to be 2.45. Therefore, for the 5 kilogram mass, it starts off at rest, U is 0, A is 2.45, S equals 0.5, the distance it travels before it hits the surface. Find V. Substituting our values in, that is 1.56524, etc. That's the speed with which the 5 kilogram mass hits the surface, but it is also the speed that the 3 kilogram mass has at the point when the 5 kilogram mass has reached the surface. Now we're in business. The 3 kilogram mass has a velocity now of 1.56524 meters per second, and the string has gone slack, so it will be travelling freely as a projectile. So that's its initial speed. The acceleration is negative 9.8. Remember, there's no acceleration in the system anymore. The string has gone slack. Velocity is 0 when it reaches its highest point. And we want to find the distance it's travelled as a projectile. So using v squared equals u squared plus 2as, substituting our values in and rearranging, we end up with s being 0.125 meters. That's the distance, just this little distance here, from the point where the 5 kilogram mass hit the surface to the point where the 3 kilogram mass stops moving and ready to come back down again. So that was just 0.125 meters. So now the 3 kilogram mass started 0.5 meters above the ground about here. It rose 0.5 meters to this point here. So the total height from the surface is 1.125 meters. In part B of the question, we want the time from the moment the 5 kilogram mass reaches the ground for the string to become taut again. And that period of time is this period of time whereby the 3 kilogram mass travels upwards as a projectile, string is slack, and then when it comes back down there, the string becomes taut again. So it's the time the 3 kilogram mass is travelling freely under gravity as a projectile. Its initial speed travelling as a projectile is 1.56524 meters per second. It's travelling freely under gravity, so A is negative 9.8. We want the time it takes to go from here upwards and back down again. Therefore, its displacement is 0, and we need to find t. So using s equals ut plus a half at squared, substituting in our values, we obtain 0.319 seconds to 3 significant figures. So to recap the important points from this last section, in this phase of motion, when the string is taut, the objects are moving under the acceleration of the system. In the second phase of motion, after the 5 kilograms has hit the ground, the lighter mass will continue upwards as a projectile.